Hello again and welcome back to the High Proton Diet. Now, does anybody out there read Elektor magazine? Well, if you do, you might have noticed that the December edition was all about Arduino. And if you turn to page 124, you can see this weird looking guy here in a hat is making a Space Invaders machine with Arduino. And it looks suspiciously similar to the one we're making here. And yep, you guessed it, that's me. And this is the machine we've been working on. So, full disclosure, first of all, this machine looks like it's finished, but it's not. It's what we call a demo. So if we look inside, all I did was I taped a joystick and a switch to the front panel. And I put in, well, I made a hole in the front to put my screen in. Remember, we had the new screen, we saw it in the previous episode. And inside was this. So we've got an Arduino Pro Mini. So let me zoom in. We've got an Arduino Pro Mini, and I soldered the resistors directly to the PCB. I did put in a connector to connect up the screen. And I put in a battery. So I've got the battery here, battery charger, and a little boost converter to make it 5 volts. So if I switch that on, as you can see, the game runs perfectly. So I just stuffed all that inside the box, took a picture, and magazine article. Okay, but obviously the game doesn't play, there's no sound yet, and sound is what we're going to look at in this week's episode. So I've got my speaker ready. All we need to do is get the Arduino to talk to this and make the sounds for the game. So, sound is an analog thing, and Arduinos are digital things. So how do we get an Arduino which can only output 2 different values, either 0 or 5 volts? Well, we use a thing called pulse width modulation. So what we do is we connect on one of the Arduino pins, we output a signal, which is some of the time at 5 volts and some of the time at 0 volts. So imagine we put it at 50% of the time at 5 volts, 50% of the time at 0 volts, and we keep on doing that. If we average that down, we get 2.5 volts average. Okay? And if we do 10% of the time at 5 volts, 90% of the time at 0 volts, then we get 0.5 volts average, 10% of 5. And we can do 80% of the time up here, 20% of the time down there. That gives us 4 volts, etc., etc. And this is something we do all the time. I think most people who have an Arduino have done this. If we connect up on the potentiometer, we can control the brightness of an LED. So I can turn it down, turn it up. And it appears we're controlling the brightness of the LED, but what we're actually doing is sending it pulses. And we can see that if we get an oscilloscope. So I've connected up this oscilloscope to the LED pin so we can see the signal that is being sent to it. So when the pulses are narrow, the LED is quite dim. We make the pulses wider. The LED gets brighter and brighter. Okay, so that appears to be an analog value, but it's not. It's just the human eye, which is quite slow, which is seeing the average of these pulses. And if I zoom in a bit, we can see here that the Arduino is putting out 490 pulses per second, which is quite fast enough to fool the human eye. But it's nowhere near fast enough to produce sound. So the next thing we need to do to make sound in an Arduino is to speed up these pulses. So for sound, we need these pulses to be as fast as possible. So how fast can it be? Well, an Arduino runs at 16 megahertz, as we all know. And each of these pulses has 256 different steps inside it. So 16 megahertz divided by 256 gives us 62.5 kilohertz pulse rate, 62,500 pulses per second. Here we have the original program for the LED. What I'm doing is I'm reading the potentiometer using analog read, and I'm using analog write on pin 3, the value I got from the potentiometer. Okay, and this function, as we saw, produces 490 pulses per second. Okay, so what I did was I rewrote the program, and now it looks like this. So in the setup function, before we had nothing, but now we have these 3 lines of code here. First of all, we set the pin 3 to be output, and then here what I'm doing is I'm programming the chip directly. There's a thing inside the chip called timer 2, and that's what produces the pulses on the pin. So here I'm programming timer 2 directly to set it to the fastest possible PWM output, which is 62.5 kilohertz. And down here we modified the program. We still read the potentiometer exactly the same, but now instead of analog write, we have here analog write. So this line is replaced with this, which I'm writing the value directly into the chip, and you can download this program below. So with this new version of the program, I can still control the brightness of the LED just like before by changing the width of the pulses with my potentiometer. But now if I zoom in, we can see that we have the pulses at 62.5 kilohertz. So we've got our fast pulses coming from the Arduino. The next thing we need is an electronic circuit to calculate the average voltage of our pulses. And for that, we're going to use a thing called a low-pass filter. We're going to use, in our case, the simplest possible one, which is just a resistor and a capacitor. This is called an RC filter. One resistor, one capacitor. And I've got my circuit here. That's it. That's the whole circuit. Simple. But of course, we need to calculate the values for the resistor and the capacitor. And to do that, we need to know the sample rate of the sounds. And the sounds I got them from a well-known arcade machine emulator. And the sounds are sampled at 11,025 Hz, which just happens to be 1/4 of CD music sample rate. Go figure. So if this is the sample rate, the maximum frequency of the sound is that divided by 2, which gives us about 5,500 Hz. We'll ignore this 25. All this is going to be quite approximate. It doesn't make a lot of difference to the sound, but we need a number in this sort of ballpark. So what I did was I went online. Just let me dim the lights a little bit. I went online, I searched for RC filter calculator. Go. And this is the results I got. And I picked the second one. There's one here at DigiKey. Just let me zoom in a little bit. I went to this page. And here we have quite a nice little calculator. So we can see here we have the formulas that are being used. So if you want to know the frequency, if you know the capacitor and the resistor and you want to know the frequency, you use this one, etc. And here we see the filter. So we want a filter that works at about 5,500 Hz. And I'm going to put a resistor value, initial guess of about 3,000 ohms. Okay, because it's a good value for an Arduino. And as we saw in the previous video, Arduinos are happy when they're putting out about 1 milliamp, so 3,000 ohms. And that tells me, so in that filter, with a capacitor of 3,000 ohms, I need a 9.64 nanofarad capacitor. You can see the values here. Now I don't actually have one of those in my capacitor box, but I do have a 10 nanofarad capacitor. So I put in my resistor, ultraviolet, 3000 ohms. That gives me a cutoff frequency of about 5.3 kilohertz, which is about what we want. Now, we said before, if we set the width to 50%, we should get an average of 2.5 volts. So what I'm going to do is I'm going to set the pulse width to 50%. This is shown as this number here on the oscilloscope. And I'm going to put my capacitor in, and what we should see is these pulses will squish down and we should get the average. There we go. So we've got an average voltage shown here, close enough to 2.5 volts. And again, if I set the duty cycle to, I'm going to put my capacitor in and we should get half a volt. About 480 millivolts. Pretty close to what we should get. Now, I know what you're thinking. It didn't all go away, it didn't squish it down to a flat line. There's still a little bit of that 64 kilohertz frequency left over. And the explanation for that is that our filter isn't perfect. So the shape of a low-pass filter is sort of this. So we program in a cutoff frequency. So below this frequency, there's an area here where the signals just go through, kind of, they don't get modified. And the filter we made starts here at 5.5 kilohertz, and the slope of the filter is gradual, and it's left a little tiny bit of this signal behind. But it doesn't really matter. This bit that's left over, it's at 62.5 kilohertz. You can't hear it. Okay, this is really ultrasonic. No human being can hear this frequency. So I'm going to ignore this little bit that's left over because we can't hear it. It won't make any difference to the game. And it keeps our circuit simple. So the next step is, of course, to write a program that outputs a sine wave. And here I'm controlling the frequency with my potentiometer. So I can go from way down low and going up, and I can go up to about 8 kilohertz. And we can see a little bit left over of the 62 kilohertz pulse frequency. But as we said before, that's ultrasonic. You can't hear that. What counts is the sine wave underneath. Okay, that's the bit you're going to hear. You won't hear the little jaggy bits. And of course, the next step after that is to listen to it. So what I've got here, I've got one of these little AliExpress amplifiers. I've hooked up a speaker and a bunch of wires. I'm going to connect this up and we're going to listen to our sine wave, see what it sounds like. Pretty impressive, I think you'll agree. And finally, here's the game running with PWM sound. Anyway, some big progress this week on the machine. I got the sound working the way I wanted, and it sounds awesome. So if you like this video, give it a thumbs up, subscribe to the channel, etc, etc. And I'll see you next time. All that from a simple pulse wave. Can you believe it?